Mics are live. There we go. There we are. Hello, everybody. Welcome back to Future in Space Hangout. I think this is our first one of the year, 2019. My name is Tony Darnell from deepastronomy.space, and today we are going to be talking about building super large space telescopes, not JWST. Will be good that we got that one covered, but the ones in the future, the bigger ones, the large diameter objective ones, we're going to be talking about building them in space using robots, people, and all kinds of other stuff, because it is an engineering problem that is going to be coming up soon. Now, this hangout is a government shutdown affected hangout. My good friend and co-host Harley Thronson from NASA's Goddard Space Flight Center is unable to attend this hangout due to the government shutdown because he's prohibited from representing NASA while he is on furlough. So he will not be in here. However, Harley, from me to you, I miss you. My thoughts are with you, and I hope this thing gets over soon, because you're going to see the quality of our future in space, we hope, is not suffer too much. But Harley's not here. I just thought I'd tell you that right off the bat. I do have the Royal Canadian Mounted Police gravitational wave rubber ducky on hand, although it is not bookended by his. So this will be, as I said, we will be suffering. So Harley, my thoughts are with you, and I know that, and even though he was on furlough, he still put together this hangout with our guests. So let me bring up my panel here. While I don't have Harley, I do have my good friend Dr. Alberto Conti from Ball Aerospace joining us again in Boulder, Colorado. Hi, Alberto. Welcome. Can you hear me? Oh, he's frozen.
Yep.
Oh, great. Okay. Because he's looking
down.
Like
so, Tony, I don't know if you can hear me. Oh, yeah. Interesting.
Oh,
sorry, my connection is going up and down.
Wow,
sorry,
that was
Tony.
weird. That was weird. So you know what it did? It buffered your whole thing. You were sitting here like this for a long time, and then all of a sudden, and then it all came out at once. Hi, Alberto. Welcome back. It's good to see you again, my friend. And he's frozen again. Oh man, this is gonna be funny. All right.
Sorry.
All right. Are you there? Are you there, Alberto? Okay. Well, all right. My guest today.
That's not good.
There he goes. My guest today is Dr. Bradley Peterson. He is from Ohio State University, and he's a did you say a fellow at Space Telescope, or are you
visiting astronomer?
Visiting astronomer at Space Telescope Science Institute. And welcome, Bradley. It's good to have you on our hangout. And he just went away. Alberto did. So it's just the two of us now. So we are going, like I said, we are before we get into our topic today, which I hope we will get your patience with, because several of our guests had last minute cancellations and could not attend, but we decided to go forth anyway and continue with this. Hi, Alberto, are you there?
Hi.
Now I know he's got bandwidth in Ball Aerospace.
Sorry, for some reason my Wi-Fi here it's been up today. Sorry.
Oh, you're on Wi-Fi? Oh, okay. Well, next time, yeah, that's part of the problem. Okay. Yeah, you got to be on Ethernet to really.
It worked perfectly last week, or 2 weeks ago. Whatever we did.
Okay, right? Well, let's hope that you're not like having a convention or anything there, are you?
No.
Okay, or like not a convention, but a workshop.
The government. I was going to say that the government is partially shut down. Not everybody in the government is shut down. That's a big distinction, but it affects all of us, particularly because NASA is part of that partial shutdown.
Yeah, but you know what? As far as I'm concerned, if NASA is shut down, it's the whole government, because that's all that matters to me. I don't really care. I do care. I'm kidding. I do care, but yeah, NASA is big, and they do. But the effect of the shutdown though is that the critical operations are still happening. The Hubble Space Telescope, for example, is still being operated. And as far as we know, the James Webb Space Telescope is still being built. It's still going forward at Northrop Grumman. So that's not being delayed anymore. So that's happening. So, but, still I feel like, with our colleagues and friends at NASA, It's a tough time, and
It is a very tough time for lots of them, and so we talk to them. Most of them are personal friends, and so we really big shout out to them. Hopefully, everything ends soon. So.
Yeah, exactly. So Harley, our thoughts are with you, and hurry back, man. All right. Well, today's topic we're talking about constructing, assembling large space telescopes. Using a variety of different means, whether it be robotic spacecraft, whether it be human beings in space. And we had several other guests from different, there was maybe Bradley, you can give us a little bit of a background on this, but I think there was a workshop held, or there's some work being done on this topic as a whole, but you're interested primarily in how it affects the mission coming up that's being considered in the next decadal survey, the Astrophysics Decadal Survey. One of the missions there is LUVOIR, which we've talked about several times on our Hangout before, and I think that's your primary interest. But is there, there's general work being done, right, by others? I think Gordon was involved in things like that, correct?
Yeah, basically we've been looking at concept studies for assembling in space. My interest in this came from LUVOIR, of course, but I was interested in how we're going to service a telescope that's in space. LUVOIR is designed to go in an SLS Block 2. It's the biggest telescope that you can fit into a Block 2 fairing. So if we're talking about single launches, this is the biggest telescope that you'll ever have in space. So we started thinking, though, when we started thinking about how we're going to service this, we can't build something this large and this expensive and then just abandon it after a decade because we've ran out of station keeping fuel or something. That's just, as far as I'm concerned, that's just irresponsible. So we had to think about how are we going to service it. And now, once you start talking about servicing telescopes in space, it's not much of a leap to go to assembling them in space, because we have assembled things in space, like the International Space Station. So we have every reason to believe that if we have something that's reasonably well modularized, we should be able to turn it into an operational telescope. So that's a part of the reason that we were doing this. But then we started to ask ourselves a somewhat deeper question. That when we are looking at deployments of JWST and LUVOIR, the autonomous deployments are complicated and risky. And we started to ask ourselves, well, what if we actually had these go up as components and assembled them in space rather than had an autonomous deployment? That could be less risky. We would have to only ruggedize components against launch stresses as opposed to the entire observatory. And you quickly start seeing that you could find a number of efficiencies that might make it cheaper or less risky, or both, for even smaller telescopes. So that's we want to know at what price point or what aperture telescope does it pay to start thinking about assembly in space as opposed to auto deployment.
And what do you think that might be? What is that? What is that aperture? Is there any consensus?
That's why we're doing the study right now.
Okay, so you're still doing that work. Well, let's take a quick step back and talk a little bit about JWST then. This is something both of you know about, and that can be our baseline from where we start. So JWST, when it's launched, will be the largest telescope, actually the largest anything, maybe next to the International Space Station, that we've ever put up in space, right? And this thing had to be engineered like talk about origami. I mean, the thing is folded in all kinds of different ways to get it to fit into an Ariane 5 rocket. So and Alberto, can you remind me what's the diameter of the objective?
So it's 6.5 meters, but actually, to your point and to what Brad was discussing, the original idea for JWST was not 6.5, was above 8, right? Which was then descoped because indeed you have in a particular shroud for the Ariane 5 in this case, you're going to have all these deployments that Brad was talking about. So there's all of these requirements that finally dictate exactly what you're going to come up with, right? So I think what Brad and the group was doing was trying to look at how do we break some of these paradigms. What is the maximum size, if you will, you can fit in a rocket that requires you to just say, maybe I should assemble it.
And it sounds like, Alberto, with the current Ariane 5 technology, the biggest you could get was 6.5 meters.
Yes, right. That's right.
Okay, so anything bigger. So what are then the big factors in limiting the telescope size? The rocket is it the biggest thing?
It's the diameter of the fairing that is primarily the limiting thing. Of course, you also run up against mass constraints as well. It's interesting to note that this JWST, and Alberto, you can correct me if this is incorrect, but I believe that JWST is something like half of the weight of Hubble, despite the fact that it's a 6.5 meter telescope and Hubble is a 2.4 meter telescope.
Oh, that's interesting. I didn't know that.
Absolutely. That's 20 years of technology, right? That's right there.
Right. So the composites, I forgot the metal that was used. Beryllium, is that right?
Yes, beryllium. That's
beryllium.
Right.
Beryllium is actually pretty heavy, but it is honeycombed, right? This technology allows you to remove 94% of each of the masses of each of the segments, right? That's what's different, right? Hubble weighed 11 tons. JWST is about 6.5.
So the beryllium actually had to do with it's a material that has a low coefficient of thermal expansion at 40 Kelvin. So it retains its shape at 40 Kelvin.
Yeah, and it's great as opposed to, originally on JWST, just to give an idea, they did trace studies between beryllium and ultralight, what's called ULE glass, basically.
Yes. Mm-hmm.
And they came up with beryllium because of all the properties and it's great. But beryllium had the added problem that it was too heavy. And so, again, technology development on how you actually remove that mass that you don't need while retaining stability, figure of merit, and so on and so forth.
Okay. Hang on. I just remembered. I forgot to say that these Hangouts are sponsored and endorsed by the American Astronautical Society. And I want to thank them for their support throughout the years on getting these Hangouts to you. They are interested. Their membership is full of companies like Alberto's Ball Aerospace and others that contribute to aerospace and robotics and all astronautics of all different kinds. And so they are the ones who sponsored this Hangout. And also I think I'm streaming on YouTube, Twitch, and Periscope. I'm not doing Facebook today, but I do have all of the chats conglomerated right here in front of me, and I'm already looking at the YouTube chat, which is the most active right now. There is also a Discord server for Deep Astronomy. If you look in the link in the description box, you will see that link to also join us, where that chat is up 24/7 and it doesn't die.
Thanks, Tony. I failed at being Harley.
What's
Harley
that?
Is the one I remember. I failed at being Harley because Harley is the one that reminds us.
Well, we got to talking about the shutdown, and I forgot my spiel. I had to say who the sponsor was. It's my fault, not yours. I got all distracted by the shutdown talk and got kind of bummed out. So
thank you.
Anyway, okay. Now, would you guys say, so before we leave the topic of JWST, which has already been designed, we're pretty confident it's going to be deployed. That was me knocking on wood. Would you guys go so far as to say that based on current rocket technology, which is the biggie here, JWST is about the biggest we could do? Or do you think we could really do any bigger?
You mean as a single launch?
As a single launch.
Yeah, I think this is the limit.
Okay, so anything after this?
Just so you know, there have been studies that you can, in principle, I think Lee Feinberg and others have done this at Goddard, you can, in principle, fit probably a 9.2 meter in a fairing of Ariane. But that requires this. You can imagine, JWST has these two wings. You can imagine another set of wings that fold again. But that has some additional requirement, which is, you have to be able to test a 9.2 meter telescope in some chamber, which we don't have anymore. Goddard was chamber A was the largest we could have used. So there's other things that might make JWST indeed one of the largest we can launch.
I should add on to that too, that LUVOIR is studying a smaller telescope, one that's about 9 meters as an option. And that one is designed to go in a generic 5 meter fairing. Yep. But the trouble with current launch vehicles is we have a mass problem. So that can be solved by a lot of light weighting, but light weighting increases cost. So right now, we're not in a great position, but if the SLS goes forward, we'll be okay.
Right.
Okay, so the SLS is something that let's get back to that one in just a sec.
Sure.
So with the current, so JWST will represent the largest space telescope that we've ever launched to date. But the decadal survey, the National Academy of Sciences is looking at all the future. They look ahead, and I think JWST was part of the 1990 decadal survey, wasn't it? So you're looking ahead to the next generation of space telescopes. Now, immediately after JWST are things like WFIRST, which is not a big telescope. It's not physically, doesn't have a big aperture. And then, but LUVOIR, if it's selected as one of the missions, would host, as you say, an 8-meter. They have two versions. They have an 8-meter version that can go up in a standard fairing. But what's the other version that they have?
The ambitious version is a 15-meter that would go up in an SLS Block 2.
Okay. And that is substantially larger because the astronomy and the science that we need to do requires it, right, guys? I mean, JWST is going to do great. We're going to see the first stars, the first galaxies. But LUVOIR, which stands for
Large Ultraviolet Optical Infrared Surveyor.
Oh, I was going to impress everybody, but then I was going to impress everybody, and then I totally blanked out, so I blew it.
It's all right.
But that's a UV telescope, which is important. It's optical and infrared, all the wavelengths, which is
in other words, it sort of has Hubble type coverage,
right?
Yes, and so
but about 100 to 1,000 times as sensitive.
Exactly, because it's got this huge prime rate. I'm going to show this animation. This is the LUVOIR beauty shot. That it's just an animation of what the telescope will look like. I'm showing it now. Do you want to describe it to us, Brad, just a little bit?
I'm having a little trouble.
Okay. Okay, yeah, it's fine. We can.
Yeah, I can't see it right now, but I can describe what you're seeing.
It looks a lot like a really big JWST.
Yes, it does. It has has segmented mirrors. It has two wings on each side that fold back. It has a sunshade, which is very large, about I think it's about half the size of a football field. But it's only 3 layers thick. It's really to stabilize the thermal environment on the down sun side. It's not part of a cryogenic system like the sun shield on JWST. JWST is intended to passively cool to 40 Kelvin. We just need stability. So we will, in fact, put LUVOIR behind 3 layers of sunshade, and we will use heaters to keep it at 265 Kelvin. Want it at a high enough temperature that water won't condense on it.
Okay. So when you say stability, you mean thermal stability. You mean
thermal stability.
No large temperature swings.
Exactly. Because those result in mechanical distortions.
Now, in the ambitious version, how many mirror segments are there?
Oh gosh, I can't even remember.
There's a bunch.
There's over 100.
Over 100. And JWST has how many, Alberto?
18.
So we're talking about quite a difference here.
Hold on a second. But we have known how to do this on the ground very well. Because, if you think about TMT or GMT or things like that, where we build large segments, right? Like I think TMT is going to have 572 segments, right?
Right.
So we know how to build those, So I think the issue is not building them. The issue is, qualifying for space.
Yes. Because we've done this on the ground with Keck.
And Keck too, as well. Absolutely.
And so and I'm just going to show this real quick because I can, the Hubble versus LUVOIR animation here. This is an animation that shows first the Hubble Space Telescope.
It has a soundtrack too, if you can turn that on.
Oh, I turned that on.
All right.
Yeah. Does it have sound?
There's
Hubble, and then like the Death Star above it, or not the Death Star.
It's
Death Star.
Not the Death Star. What was it? The Star Destroyer. Star Destroyer from Star Wars.
But the soundtrack is the Imperial March.
Yeah. Yeah. I don't have that queued up. But look at that difference. I mean, it is quite a huge. This telescope, to me, I mean, I know there's 3 other really great projects being considered for the decadal survey. This one and the exoplanet one are my 2 favorites, I think.
That's right.
Yeah, this one. So that's the side. That's to give you some scale, folks, of what we're talking about here, and it's going to fold and all of this kind of stuff. Okay, so let's get. And you said, Brad, that this design, the ambitious one, Not the 8-meter one, which nobody wants. We want the big one now.
Yeah, we'll settle for an 8-meter telescope.
Well, I suppose, but yeah, I want the biggie. You're saying that the planning for LUVOIR. I understand it's early yet. You can't go too far into this until you get selected as a project or as a priority. But what's going to be the way to go about this, getting this up? You said the SLS is involved. What are you guys thinking?
We've basically been instructed by NASA to assume that SLS will be available.
Oh, they're telling you to use it.
That's the assumption for the study.
I see.
Okay. But we are also doing this separate study. It's a separate group of people looking at assembling telescopes, and that'll be a nice backup if it turns out that the SLS is not going to be available. Then we're looking at assembly in space.
Okay. All right. So what I'm sorry, I'm embarrassed to say I was looking at a chat. You said that if that's not available, if what's not available, it will be.
If the SLS is not available for LUVOIR,
okay,
we could still build something the size of LUVOIR using in-space assembly.
But you're still not planning with SLS to just launch it in one shot, are you?
Yes, we are.
Oh,
SLS is yeah.
Oh, again, I see. I misunderstood.
We did have instructions from NASA on this. That I asked. That was one of the first questions I asked Paul Hertz, who's the director of the Astrophysics Division, when I was commissioned to do this. I said, "How many launches do I get?" And he was very quiet for a moment and said, "1, but you can assume it's an SLS."
Right.
Does that scare you at all? Would you rather have it several launches?
Either is challenging.
Yeah, I agree.
Yeah, I mean, one thing about an SLS launch is going to be the single launch is going to be very expensive. And you have the whole mission then riding on one launch. So
that's right.
If you're not doing in-space assembly, loss of launch vehicle is loss of mission.
Mm-hmm.
Yeah, that's a pretty big deal.
Plus, there are there are other sort of industries coming up. The SpaceXs of the world and the Blue Origins of the world that might have large fairings. SpaceX has the BFR, Blue Origins is going to have something. The New Glenn is probably 7-meter fairing. Mm-hmm. So you could, in principle, think about amortizing launches using different kind of providers, if you.
Yeah, and the medium launch vehicles are there's a market for those, and the market is likely to have prices driven down, and so we may reach a point where we'll say in-space assembly is just going to be so much cheaper, right. But what we still need is infrastructure in space to do that assembly. So that's the one thing that we haven't costed out yet.
Okay, is LUVOIR going to go to L2?
Yes.
Okay. Before I get to specific questions that people are asking on the chat, I know that we had other guests and they couldn't make it, so and I don't mean to put you guys on the spot. If you don't know, just say it's no biggie. But let's look a little bit further past. Now there was the high definition space telescope. It's been renamed into something else now.
Yes.
These are way down, 2040, 20. I don't know how far down. But
actually, LUVOIR is a direct descendant of the high definition space telescope.
Is it? Okay.
Yeah.
So what the bigger ones, what do you know about? I mean, I've seen things like star shades that are enormous and gigantic and are probably going to have to be origamied up into space. So I guess my question is, the ones, do the far future ones, they're going to have to be done in several launches, right? Or do you think
if it's over 15 meters, there is no other way.
There's no other way after 15 meters. Okay.
Yes.
And we already talked a little bit about the cost point. We don't know where the break even point is for breaking it up into smaller launches yet.
Right.
But
as Brad said, I think it depends on two things, right? One is can you launch? How big can you launch? How big of a segment, let's say, of a telescope that you want to put in space, you want to launch? And then the second thing is, when does it make sense from a cost perspective, to do that, and how many launches you need, right? So you have to do all this stuff. And then, as Brad pointed out, there's no infrastructure right now where you can, so you can launch pieces of a large telescope, and then what, right? Right. So there's a lot of discussion about gateways, and at some point, you can imagine I can imagine, I can envision taking the core 12 segments of James Webb Space Telescope, which is a very well-defined piece of hardware, if you will, and launching multiple of those that can then be assembled in space to build a larger telescope, for example, right? But then, and I believe we could actually even do that right now. But the problem is there's no infrastructure that can, can acquire these pieces and then put them together either robotically or with humans, right?
Right, and
that's a big one.
Did you want to add something to that, Brad? Go ahead.
Yeah, that's really the key issue. And I think one of the things that got me to thinking, we can really do this, was when NASA started talking about this deep space gateway that was going to be orbiting the moon. The great thing about this is the delta V to go from cislunar space to Sun-Earth L2 is tens of meters per second. Right. It's practically nothing. So, there you've got a very natural place to assemble and service as you're orbiting the moon. And when you're done, you can do all your testing. And then once it's tested and verified, then you send it on its way to Sun-Earth L2.
I'm so glad you brought that up, Brad, because I don't know what it is about that gateway, but every time I talk about it on these Hangouts, there's all these angry comments coming that they just don't, that people just don't like it. And to me, that's a great, absolutely perfect use for something like this, folks. I mean, I get it. You want to go to the moon, you want to go to Mars, don't screw around with this gateway business. But I actually think it's a good idea. I still think it's a good idea because it is a good way to work out a lot of the technologies that we're going to need, not just go to the moon and Mars and all that stuff, but think about the space telescopes in L2 that we're going to need to put there. This would be, would you say the delta V was tens of meters?
Tens of meters per second.
Right. So, I mean, that to me, that by itself, nothing else makes it worth it to explore this gateway idea.
And to me, that's equivalent of building a telescope someplace and then moving it to its operational place, right? With very little energy, and that's makes a lot of sense.
Yeah. Right. You can use an ion engine too, so that the accelerations are very gentle, and you don't have the whole telescope ruggedized against launch stresses. It can actually be pretty fragile.
Yeah, the universe is the limit, folks.
Yep.
The universe is the limit. All right.
Well, you do have to survive launch. The segments have to survive launch.
Yes, they do. Right. But that's different than the entire structure.
Absolutely, very, very different from lots of and astronauts have to survive launch too. So if they put it together.
So getting to your point on the infrastructure, this probably would have been a good question for Gordon, the guest that couldn't make it. He works for a company, by the way, folks, called Robots in Space LLC. Okay, so chances are, and we have had hangouts before where Harley and I have talked about companies who's working on the technology to like go up and fix satellites in Earth orbit, they're developing the technology now to launch a robot, go to a satellite, grab onto it, fix it, replace a component or something, and then leave it up or maybe push it up on a higher orbit. That's a thing now. That's a business opportunity that corporations are actually looking at seriously. And so it isn't a big stretch then to go from that kind of technology to building robots that are maybe permanently stationed up there, maybe in a gateway, and can build things up there already in space.
Yeah.
Do you guys know? I mean, I know this isn't your expertise, but can you comment on any of this? Is this stuff being built now? I'm sure it is. Some of these infrastructure issues.
I can tell a little story.
Okay. I love stories.
It's a quick story, quick personal story. I gave a talk once about James Webb, and I was talking about future telescopes and LUVOIR and larger telescopes. And I said, if we're able to build telescopes in space with robots, and as I was saying that, if a 15-year-old from the audience raised his hand, and he said, "What do you mean if? I've been building quadcopters since I was 12. Of course we're going to do this, right?" And that changed my whole posture, which is like, why do we even think that if, it's just a matter of when? And I think the infrastructure is just going to exist. It's just a matter of when. It's not a matter of if.
I don't think it's a question of technology or innovation or any. I just think it's a matter of political will if it's a government doing it, or making a good business case if it's a business doing it.
But space is hard, right? I mean, space is hard.
Sure, it is.
But the environment is non-forgiving.
But
right?
think of the profit you could make repairing communication satellites instead of having. First of all, you're saving other corporations millions and millions of dollars by fixing something that's already up there instead of launching an entirely new satellite. So the business case is there for the repair part of it. Now imagine you can make a business case for building things up there. And I think you could. I think you could make that case. And I think the issue really isn't ever going to be, can we do it? Technically, yes, we could do this, but it's always a political question. Can we politically pay for it and all that crap?
Right. There's another aspect to this as well regarding the infrastructure, and this really comes down to money. And the question is, does the NASA Science Mission Directorate have enough resources to be able to do a service mission without basically gutting everything else that it does?
Yeah.
And for that reason, I think it's important that this has to be an agency priority, and the way that you make it an agency priority is you bring in human exploration, because you can solve a number of different problems by using humans to assemble or to supervise robotic assembly.
So you're saying as part of the infrastructure plan for this kind of situation, humans should be a big component.
I think they should, and for the practical reason that we really need agency-wide support to make this happen. This is the sort of thing I think that the manned program would like to do, because it's very high visibility, and it's good use of astronauts. Because, well, one of the things we've learned in Hubble repair missions is that sometimes flexibility is required, and things aren't always the way that we imagine that they're going to be, and you have to sort of make it up as you go along. And humans are much better at doing that than robots. Robots, of course, have other virtues. You know, they're infinitely patient. They don't care too much about how hot or how cold it is.
Right.
And they're capable of high precision motions. So I would think that some combination of these things, where you make use of the better qualities of both types of servicing.
That's a good point. So, Alberto, what do you think? I
was gonna say one other thing. So, astronomy. I'm gonna be a little biased here because of my profession, I guess.
Me
but
too.
Astronomy is a little. We all do, yeah. Okay. But so astronomy requires. So I think from a commercial standpoint, you're right. I think things are going to happen, repairing satellites and everything else. When it comes to astronomy, though, and astronomical applications, there's some cleanliness requirements, right, that you don't think immediately about, right? The environment, for example, around the station is pretty dirty. There are like fuels and things, and so you have to be a little careful when you don't want this dirt, quote unquote, to go on your pristine mirrors that you spent 8 years polishing, right?
Well, if you're using the gateway as an assembly point, you're not likely to actually be in immediate proximity to it. Yeah,
correct.
Just as a safety measure primarily, but also for contamination reasons. And you're certainly not going to have the Deep Space Gateway actually dock with something, say, the size of LUVOIR.
Correct.
Because the mass differences. You'd have the tail wagging the dog is what you'd have going on.
Whoa, I can't hold on to this thing.
Yeah, but the analogy, I think Marty Frederick used to work with me at Northrop. I had this analogy, which I thought was really good, which is the moment humanity discovered elevators is that when we started building very tall buildings, right? And the elevator is just an enabler. So we need that infrastructure that is ready for us to be able to build these things, right? So we need the elevator in the sky. How's that?
Agreed. And I think that's an important point. And unfortunately, our guests aren't here to comment on that part of the discussion, but that is key, is to be able to set this infrastructure up for building these telescopes or whatever it is.
I don't care if it's a gateway or something else or whatever comes up, but that infrastructure has to exist for us to be able to build these large structures that we can build on Earth, but then we can launch them, right?
Okay, let me ask a couple questions here that people are leaving in the chat. First of all, Hans Milling is leaving a comment that says that the Starship, which was formerly the BFR, can take huge things, which is true. And I think you mentioned that too, Alberto. Yeah. So Neil Yu wants to know if LUVOIR could compare to a few small linked terrestrial planet finder scopes. Let's say we put some together via interferometry or whatever. Well, maybe we should comment on what the science of LUVOIR is supposed to be, first of all. Maybe we should talk about that.
Yeah, this is science always wants bigger apertures. You just need the larger collecting area, and you'd like to have diffraction limited optics, because when you do those two things, your sensitivity to point source detection goes like the diameter of the fourth power. So even a small increase in your aperture has a big increase in your ability to detect faint things. So in the case of LUVOIR, what we want to be able to do is look directly, image, and take spectra of exoplanets in the habitable zones of nearby stars. So you need your larger aperture so that you can observe the habitable zone of stars which are increasingly further away, so that you have a large sample. So that's what drives LUVOIR to the 15-meter sort of size, because at that size, you expect to detect and observe enough exoplanets that if you find no traces of habitability, then you have ruled out habitability in the local neighborhood at the 95% confidence level. If you can only detect one or two systems and you don't find anything, a negative detection tells you nothing at all.
That's right. That's an
so
excellent point.
that's why we want a telescope in the 15-meter range, because then we can do statistics that mean something if we don't find anything. If we don't find anything, 95% confidence, it's not there.
Right. And Brett and I would like to know in our lifetime. We're getting older.
You're getting older. Oh, I know.
I'm getting very old. Yes,
Yeah.
but the issue is this. I mean, you can know, with a telescope like that, you would be able to address that question within our lifetime, right?
Okay. Well,
and because of the collecting area, and because of the diffraction limit, and the way the inner working angle works out for exoplanet detection, this is not something that's easily done with interferometers. It's much better done with large collecting area.
Right. That's a good point. Condor Boss has a good question. He's asking, I wonder what the practical limit on the size of a space-based telescope would be. What would be a practical limit, and what would be the thing limiting it? Things like tensile strength of the cradle could be a big factor. How big do you think space telescopes could get? Just your opinion.
The telescope that we're looking at right now for in-space assembly, and we're doing this as an engineering exercise. We wanted to make it bigger than LUVOIR so that it was clear that this was not LUVOIR that we are redesigning. Mm-hmm. And also, we wanted something that we could scale down so that we could see where the price breaks are for various price points. And the size that we're looking at is 20 meters. And if you look at a 20-meter telescope, we found that we've done, again, concept studies on this. We can break it into about 70 segments, and it would require something like 10 to 12 launches. So 20 meters, what we found in studying the 20 meters is we have identified no showstoppers, which really amazed me. We have had basically each time we've had a meeting, we've sort of broken into 2 or 3 teams and had them go do a preliminary design and come back tomorrow. And showstoppers have not been identified. There wasn't anything they say, well, no, this is prohibitive. We can't do this. So we know it can go to at least 20 meters. Now, when you get beyond that, then you start having to worry about things like the strength of materials and control systems and control surfaces. I don't know what the limiting factor would be. I haven't gotten that optimistic yet that I've run up against a problem.
Right. But in principle, I guess if you can modularize things, right, and then figure out a way to have an infrastructure to assemble them, the limit is probably, I don't know. I don't see material limits, actually.
No, well, on the ground, the Europeans were looking at building an extremely large telescope, and once they got about 50 meters or so, then you run into some problems that simply cannot be solved. One is wind loading.
That's it. That's
and I think it's also, at some point, you sort of exceed the size of the isoplanatic patch in the atmosphere so that you can no longer do adaptive optics.
Yeah.
So you've just got a big light bucket.
Yeah.
Right. Okay.
But ultimately, you can think about if segmented is indeed the way to go, then you can build, each segment can be a unit, and you can assemble thousands of units or something. Maybe they're independent. Maybe you put them together in some way or something. I don't know, right? So the limiting space is very different than the ground, as Brad mentioned, right?
It's probably simply going to come down to cost.
Right, yeah, which is the variable we're not talking about.
Yeah, the number of launches, all of that. I mean, so all of that adds quite a bit to the cost. Another thing I think is a limiting factor, maybe not to building the telescopes, but maybe to using them, and that is the fuel. I mean, correct me if I'm wrong, Alberto, but so JWST, I think's mission is 5 years nominally with a goal of 10, right?
Yeah, 10 or plus. Correct.
10, and a limiting factor, of course, is the propellant.
Right.
That's on there.
But JWST is the propellant not just to control the attitude, right? Because he acts like a solar sail, so he wants to kind of tip, if you will, right, in one direction. So you need to control the attitude, and you can manage the attitude with gyroscope and reaction wheels up to a point. And after that, you have to dump some momentum and you fire the little thrusters. And so how well you manage the momentum dictates basically your lifetime, including your initial orbit and so on and so forth, right? But yes, so there's a limiting factor, which is fuel in managing your.
I mean, it killed Kepler. That's why Kepler's not still taking data. So
right. And the other thing is L2 is it's an unstable orbit, so there's a certain amount of station keeping that is required.
Always required. Correct.
Yeah.
Correct.
Another limiting factor I see in a lot of these telescopes, I know that building them, if you're going to spend all this money and time building ginormous telescopes, using them for the longest amount of time is a good thing. I think detectors are another thing that's going to limit the life of these missions, because they degrade.
They do. Exposure to cosmic rays causes them to degrade over time.
Yep, and so
But that's why you make serviceable telescopes, right? So you swap things in and out.
That's true. Do you think NASA? I know, right? Well, let me just ask you, Brad. Is LUVOIR under any constraints to make LUVOIR serviceable in any way?
Well, actually, there is a law that says that we must make it serviceable.
That's what I wanted to hear. Yeah, I wanted you to say that.
Yeah, and whether or not it gets serviced is a separate question. But we're making it serviceable. It's all the instruments are designed to be easily swapped out, and I think basically everything will be replaceable except the optical telescope assembly itself.
Easily swapped out by whom?
Robots or astronauts.
Okay, so you're doing them.
And if it's at L2, robots. If we can bring it back, then possibly humans as well.
So you don't think we're going to have human capability out there anytime soon?
I think it's a dangerous place to go, because unless you want to burn up an enormous amount of fuel decelerating when you arrive there, you're going to have to take you on a trajectory that takes a long time to get there.
Yeah, I should mention real quick that the L2 point is 1.5 million kilometers away from Earth. It's a point that follows the Earth around its orbit around the sun, and it's a good way to see both the moon and the Earth.
We should indeed ask John Grunsfeld if he would be willing to, astronaut extraordinaire, if he would be willing to.
I would love to have it. We need to definitely get him.
I have already asked astronauts how they feel about going to Sun Earth L2, and they're, yeah, baby, when do we go? Exactly. That's the way astronauts think. Those are the people you want flying.
I agree.
I don't think astronauts are never going to say no, are they? If you say, do you want to go? They're not going to let you finish the sentence. They're going to say, yeah, I'll go. Where are we going? They're never going to say no. I don't think anyway. Okay, so let's see here. Galaxy is commenting, I still prefer the telescopes of the future and discoveries like life and direct imaging of planets in the future. Hans Milling is commenting, if you assemble in space with no gravity, the size can be as much as you can afford, I guess. And that's what we were just saying. It comes down to money, really. Only at some point it will turn into a giant solar sail and get blown away by the sun. That's a good point, too.
Yeah, that's a good point, too. Exactly. That goes back to your point about fuel and attitude control and so on.
And
momentum management.
Neil Yu wants to know if we have any idea how much is being spent on robotic space assembly by NASA or by anybody, I guess. Do we have any idea? It's not really. Unfortunately, we don't have our guests that specialized in that, I'm afraid.
Yeah, I don't know, actually.
Yeah, I haven't. Nothing.
Yeah, not enough. Larry Keys, is the driver at 15 meters for the it's for the LUVOIR, I think. Yeah.
Mhm.
Hans Milling, if Bush had not canceled NASA's Mars program, we would have humans on Mars by now. But they are back on track, and so was SpaceX. So hopefully in my lifetime, I will get to see humans on Mars. You guys have a comment on that? Do you think we're going to see them anytime soon on Mars?
We still need to learn how to live in deep space. When you get beyond the magnetosphere,
Yeah, I know.
it gets dangerous.
Another reason for the gateway, in my opinion.
Yeah,
Yeah, I agree. So you can learn.
We did a series. You guys don't know this. We did a series of hangouts a couple of years ago with Arnold Nicogossian from George Mason University, who literally wrote the textbook on space physiology. And I came away from that series of hangouts. He was very articulate in showing and describing all of the problems of human beings in space. And then I came away going, I'm not so sure we can live out there. I mean, we're going to have to really build some amazing protection for people to be able to make this work.
It's a very tough environment, and I think if you're going to Mars, you're going to have to introduce artificial gravity at some point. You're going to have to use a centrifuge, because we're finding that the physiology changes if you're weightless for like 6 months. I asked one of my friends who was on the space station for 6 months, what was it like coming back? And he said it was like coming back from a long stay in the hospital. He said it just took him a long time to readapt.
Our bodies are just not made for this.
A lot of things happen. He said that walking around became painful because he had no calluses on his feet anymore.
Wow.
Yeah, and you're used to, in the space environment, you're wearing a t-shirt and shorts that just kind of float around you. And then you get back on Earth and you have these clothes which are hanging on you and dragging you down. Just things that you wouldn't expect.
Oh, wow. Yeah.
And the muscles that you use for something like sitting. Well, you exercise your large muscle groups while you're on the space station, but there are all these little muscles that atrophy, the ones you use for balance. And, so it can be kind of a miserable experience. And it's, you don't want people arriving at Mars after traveling for 6 months and in that sort of shape.
No, you don't.
No.
And that's and that right there, Brad, is one of the reasons why I don't know. I love space exploration. I want to do it, but I don't know, man. I just don't know. We may not make this. I mean, there's a lot of unless Ray Kurzweil is correct, and we all just beam our personalities into a android body. I just wonder about our biological ability to do this, but I'm sure we'll solve it somehow with rotating artificial gravity or something, or maybe.
Yeah.
So maybe that's the solution.
I mean, come on. Everybody's seen 2001, right?
Yeah.
Yes.
Yeah.
And The Martian.
And The Martian.
Yes.
And The Martian, right?
And the only reason they don't do that now is because it's so expensive.
Okay.
Yeah, because we haven't figured out exactly. So one of the other things that that I think we should think about is also how you reduce that entry cost to actually get off Earth, because that's the biggest problem right now, right? So companies are trying to do it. NASA's been thinking about it for a long time, but that's the biggest entry.
Everybody's seen 2001, right? Yeah.
Yes.
Yeah.
Oh, I think we got Gordon joining.
Is that you, Gordon?
Yeah.
Hello.
Yes, hi.
Hey, there he is, Gordon. Welcome.
Here I am. Better late than never. I apologize.
That's very true. So this is Gordon Roesler. He is from Robots in Space LLC. Welcome, Gordon, to our hangout.
Thanks. Glad to be here.
Well, you came at actually a pretty good time. So right now, what we want to know is what is being done in the realm of robotic space assembly. What's the state of the technology right now? Who is doing stuff to build robots to get us to either assemble things in space or repair things in space? Give us an overview, if you could.
You bet. Starting with the program that I led at DARPA for 4 years, which is called Robotic Servicing of Geosynchronous Satellites, or RSGS. A spacecraft with 2 7-degree of freedom robot arms on it. If primary missions don't include assembly, they include inspection and repair and upgrade, but it's perfectly capable of doing assembly, right? These arms are 2.5 meters long. They can change their end effectors to adapt to different things. So what I've suggested at several fora, including military and NASA forums about space servicing is that to test some of the ideas we have about assembling in space, that we send experiment packages in the 2020s up to RSGS, which will be in geosynchronous orbit, so that it can prove out in space some of the assembly concepts that are going on. I mean, understand that the telescope is not intended to be in geo, right? That's not the right place for it. But you'll have an operating robot out there, and it could certainly do those experiments. NASA's Restore L mission, which is a LEO mission, has the same robot arms that RSGS does, so it could also be used.
What's RSGS?
Sorry, that was the program that I led at DARPA, Robotic Servicing of Geosynchronous Satellites.
Okay, thank you.
Yeah, thought I said that. So both of those spacecraft have very capable, very precise manipulators. The end effector errors are typically on the order of a millimeter from where you wanted them to go. So they should certainly be and they have the tool changing capability. So they should certainly be capable of doing validation of assembly concepts. In the case of Restore L and LEO, in the case of RSGS and GEO, RSGS is a 15-year life spacecraft. Restore L is a 1-year life design. So you'd have to hurry up a little bit if you want to use Restore L, but the capability is there, right? So these are two platforms that will be on orbit, will be available for doing some of these tests. In terms of what's going on in laboratories, the two leading on-orbit assembly laboratories at NASA, I think, are JPL and Langley. They've done a lot of work in structures and in automation of assembly concepts and that sort of thing. I'm trying to think if there's anything else I can point to in terms of near-term ongoing stuff. Obviously, there's a lot of stuff going on at university levels that are looking at various parts of this as well.
Now, is this one of the things we were discussing, and Alberto was making a point about needing, before we start launching these space telescopes that need to be assembled in space, we need the infrastructure. And one of the bits of the infrastructure I was trying to say was this ability to repair satellites that are already in orbit. And is that the kind of thing Robots in Space is working on right now, or is it something else? Are you guys trying to make a business case for satellite repair?
So I'm leaving the business case for satellite repair to DARPA and SSL, who are the two partners doing robotic servicing of geosynchronous satellites, RSGS. And I'm more tackling the question, what's next, right? And assembly of these things is certainly part of that. Now, at the latest NASA meeting that discussed the in-space assembled telescope, that was the one that was held at Langley, I made the point, I don't think that it's a good idea to have this telescope be the first big thing that's assembled on orbit. I mean, I think that's kind of crazy. If I was, let's say, the science mission director, associate administrator or something, I would say, hey, if that's already out there and I can leverage it, that's a great idea. But if I have to develop all the robotics and all the techniques, and
agreed.
That's a bridge too far. The budget will never support it.
Exactly.
Now, the good news is there are many commercial drivers to doing on-orbit assembly, and I'll tell you what two of them are. One of them is just building great big antennas. Those have a lot of value in delivering bandwidth, and the hunger for bandwidth on Earth is not going down. Let me tell you that. So there's going to be a lot of desire for higher bandwidth going through satellites. Large antennas will be a piece of that, and people will figure out how to build those on orbit. I know of some companies that have put some money into figuring out how to do that. The other commercial driver for on-orbit assembly is building large structures in GEO that you can hang multiple payloads on and power them and point them in the right direction and that sort of thing. So today, if I wanted to send up a commercial communication satellite, let's say for television or data exchange or something like that, the program would be somewhere between $300 and $500 million. You have to come up with that. I know that the rule was we're not going to talk about cost, but just to motivate the idea that there is a driver for on-orbit assembly, if you had a platform where you could simply hang a payload, so you don't have to launch a completely integrated satellite, but only get a payload up there, you cut the capital expense down by a factor of 2 or a factor of 3. So these are some commercial possibilities that are being looked at in on-orbit assembly, and perhaps the capabilities that are developed to do those can be leveraged for this telescope assembly.
Okay, well, that's good to know. And I love the idea of maybe not let's making our first assembly project, you know, a 20-meter space telescope. Maybe that's a good idea. Maybe make it something smaller. So Brad was telling us about the requirement by law that LUVOIR be designed to be repaired. Do you know enough about LUVOIR to be able to, worked on? Do you know enough about LUVOIR to be able to say if the kinds of robotic technology that we have now would be up to that task of replacing components? First of all, going out to L2, replacing components and putting new ones in?
Right. So you're making a distinction now between assembly and then...
Yes, I am. I've only got 5 minutes, so I've got to move way forward here.
Okay. So in terms of servicing, the primary things you'd want to do are refuel it so it can maintain its position longer, repair it if something breaks, and then upgrade it, just like we put new instruments on Hubble and that sort of thing.
Exactly.
Those are within today's capabilities, and let me give you an example on a smaller scale. In 2007, DARPA flew an experiment called Orbital Express, and it replaced a battery module and a processor on its target satellite, and those both worked. Those replacements were done completely automated without human joysticking. So we know how to replace things, and repair is the first cousin of replacement. So I don't think that the servicing is the big challenge. I think it's the assembly. Okay.
All right. And just real quick, I've only got a couple of minutes left. Are you thinking that robots can be the robotic repair and replace and all of the stuff we've been talking about would require a human component to make this really successful, or do you think we could do without?
I believe we can and should do without because of to be honest, because of the expense of human space operations.
Yeah. Okay.
If we're unable to avoid that, I'm afraid that the cost is going to again be a killer. Have we talked about risk also?
No, we don't care about that. No, we just want to do it.
We don't care about risks.
Right. I mean, there is risk to basing a program on robotic assembly. There's also risk to folding up a telescope into a single robot and launching it and praying that it A, doesn't have a launch failure, and B,
yes, I know,
deploys perfectly, right?
Yeah, I'm praying for Ariane 5 success here coming up in a couple of years. Yeah, I know just how you feel. Okay, guys, well, we're out of time, unfortunately. Everybody has to go pretty promptly here at 4 o'clock Eastern time. Any final comments you guys want to make? A couple minutes. No?
Let's go and bake something extraordinary. We need to find life. We can do this. Let's service it. Let's keep it for 50 years as opposed to the 5 to 10 years when we have typical telescopes running.
Yeah.
Well, these very large telescopes with their capabilities for examining exoplanets, we can answer the question, are we alone, in a meaningful way? And I think that's the most compelling science question that's ever been asked. And that's why I think that stakeholders like Congress and the American public will support it.
All right. Well, that's a good way to end it. I would thank you guys so much for joining us in our hangout, our Future in Space hangout. My guest today were Bradley Peterson from the Ohio State University. You're from the Ohio State too, aren't you,
Yes.
Alberto?
Brad was my professor.
Yeah. Well, we didn't even talk about that.
Ohio State. Yes,
also, Gordon Roesler from the Robots in Space LLC. I want to thank you so much for taking time out to talk with us. We will be back next week where we'll be talking about something. I don't know. It depends a lot on the government shutdown, guys. So anyway, thank you all so much for watching. And as always, keep looking up.